All right, so we're going to continue with um, curved mirrors. So here we're going to talk about how we can use concave mirror to get different images depending on the position of the object. So generally, there's this mirror equation that we can always use to calculate the value of the image position. But the ray diagrams also allow us to find the position, at least graphically, not necessarily, a precise value for the position, but approximate, position for the image, type of, image that we might have, inverted, upright, and all those things. Array diagrams, allow us to get all of those things. Um, so let's look at then the next few slides. Pretty much goes over um, several cases that we can have for the concave mirrors. So here I have three rays that can be used to find the image position. So here you can see that ray 1, which is in blue, is always starts from, by the way, all the rays will kind of start with the, the tip of the arrow, because here's, being our object. So you can see, right? So this is our object. And what we have here is the object. When you do the tip of the arrow and you find the image, you're basically finding the tip of the arrow of the image. So it will tell you if the image is upright or inverted. So then let's say we are using this point, if you want, let's say point P, right? To find, let's say, the position. All right, so that point P is used as the position of interest. And then starting from that position, then we draw this ray 1, which is always parallel to the principal axis, right? You can see that this is the principal axis over here, right? And the principal axis then goes through the, sort of like always middle of the mirrors or middle of the lenses later on. So the principal axis is used for mirrors and lenses. And ray 1 goes parallel. And you can see, right? So what you have here, the position of the object over here is such that it is in front of the mirror and is further than center of the curvature of the mirror and the focal point. That means, in a way, you can say that this is, let's say, case 1, where the position P of the object is greater than even the radius, right? Remember, because the distance from the C to the mirror is the 1 radius distance. All right. So then that's kind of what we have. That means in this case, we have object further than the center of the curvature of the mirror. All right. So ray 1 goes parallel to the principal axis, hits the mirror, and reflects back. And always it has to reflect back to the focal point. So you can see, right? So that's why. So it hits the, the blue ray, right? So goes, hits the mirror, reflects, and goes to the focal point. Ray 2 has to then go through the focal point first, and then go parallel to the, to the principal axis. It's kind of like the opposite of what ray 1 does. And you can see already, right, with those two rays, so ray 1 and ray 2, I have them intersect at that point. But then what we do, we use the third one to kind of verify that. And the third one is convenient one because, the line goes through the center of the curvature, hits the mirror, and it's always going to hit the mirror perpendicular to it, and then reflects back on itself. Okay. And then you can see, right, all three of them converge at that point. Then you draw the image, and you can see, right, image is inverted, it's upside down. Okay. And what we get here is, you can see in the picture, right, image is upside down, and it is real, right? It is real. And what we get here is, it's real again because actual rays go through that point. And when actual rays go through that point, remember, then they converge at some point. I guess we can call it P prime. and that is then, the same basically as P, but it's image. All right, so again, we'll talk about that. So you can see, right, the rays usually go in all direction from the object, but we use generally no more than 3, because with 2 we can already find where they converge. With third one we can verify that. Okay. And the image point obtained by the ray diagram must agree with the value of Q calculated from the mirror equation. Because one of the things I have here is when I use the equation 1 over P plus 1 over Q equals 1 over F, and if I calculate Q, and Q here, if you could see from the image, right, should be basically, let's say greater than focal point, right, or focal length, but less than the radius, at least for this particular picture. So if we go back, you can see, right, the image is between the focal length and the curvature. Okay, that means it's, greater than focal length, but less than radius. So that should more or less agree. Q then also should be positive because it is real image. It is in front of the mirror. All right, so let's kind of summarize this. So if the center of the curvature is between the object and the concave mirror, that means, let's say here we have doing this case 1, where we're saying that this P here is greater than the, center of the curvature, or you can say that this point C, right, is between object and the focal points, right? Then the image is real. Again, it's real because actual points converge to that, at that position, P prime. And the image is inverted, which we can see. And the image is smaller than the object. The way we can figure out, let's say, the image is real using the mathematics is Q going to be positive. The way we know that image is inverted, H prime will be negative. And the way we know that image is smaller than the object, then in this case, M will be less than 1. Okay, because if it's smaller, then it will be always like 0.6, 0.8, 0.5, 0.2, whatever it is, but the number for the magnification will be less than 1. So for example, here we might get magnification of negative point, I don't know, 0.3 maybe, because it says that the negative means that it's inverted. 0.3 means it's about 30% of the size of the object. Okay, and that's kind of more or less follows what this image represents. Okay, that means we can always, do this ray diagram, always find the image position, and then use the mirror equation with magnification equation to verify that and to get precise values. Because look, you can see, right, the image in this diagram doesn't really give you exactly, yes, it's between, center of the curvature and the focal length, but exactly where it is, we won't know until we use the, equation of 1 over P plus 1 over Q equals 1 over F. All right. So one thing we can have here is, let's say, if you continue moving the object, so kind of go back over here. So if I continue moving the object toward, let's say, toward the mirror, one of the things I will have here is then the image, let's say, image will start increasing its size, and it's going to be pretty much, let's say, real all the way until we reach, the focal point. So let's say I want to quickly give you, well, there are a few scenarios that, I want to give you, like, let's say this is case 1, right? There are a few other ones, but maybe we can do it in an example. So I have an example where I can actually kind of more or less talk about that. So, but generally, this few slides demonstrate that with the concave mirror, here an example of where you get a real image. Okay, real image is in front of the mirror. Real image is always going to be inverted. Real image doesn't mean always going to be smaller. It can actually be same size as the object or even bigger than the object. But those two at least will be always true for the real image. Real image is basically, well, the image is real if you can see, right? Sort of like if it is inverted. And if it's a real image, then Q will always be positive, H prime will always be negative. Magnification will always be negative, but it can be less than 1 or greater than 1, depending on the position of the object. Because if I put the object here, then what I will have here is the image will be there. Okay. If I put the object here, the image will be somewhere over here and even maybe bigger, slightly bigger than the object. And what happens if I put that here, the object, right? So in that case, this is what the next slide represents. So if I put the object such that P, which is the position of the object, is less than the focal length, then what we get here is, if you can see from the ray diagrams using those 3 rays, see the first one parallel, then through the focal point. That's the first one. Second one, through the focal point, but the focal point behind the object. So it kind of goes like this, and you have to trace it back already. Kind of, that's the hint. So then you go parallel to the principal axis. Same thing with this curvature, right? So you go like this, and then it reflects back toward the C. And you can see in front of the mirror, those 3 rays do not converge. They would never converge. They're actually diverging away from one another. So what do? Well, we trace them back. We'll trace them back behind the mirror. And then we can see there is a point where they converge. There is a point where they appear to be, diverging away. And that is the position of the image. And then you can see, right, the image is virtual because it's behind the mirror. Image is virtual because no actual rays go to that point. Let's say that's P prime, right? And so it's upright because every virtual image is upright. Well, upright, in a way you can think of like it's upright because it is doing the, have the same orientation as the, as the object. Okay. So it's, if the object was, upside down, then the image will be upside down for, if it's a virtual image. That means for the virtual image, the image and object orientation always the same. You can think like that. All right, so for this particular case, we also get enlarged image. That means the image always larger than the object. And you can see that in the picture right on the right. This is basically, one of those magnifiers. So it actually magnifies the image, so it gives you a much bigger image, let's say. And again, this happens when the object, right, is very close to the, concave mirror. That means close enough that it has a smaller distance than the focal length. So if you are closer to the mirror than the focal length, then you get basically virtual image. That means concave mirrors can give you real images and they can give you virtual images. Those are the two things we can get with a let's say concave mirror, where if you kind of go back and look at in terms of what we can have with a convex mirror. So remember, this is convex mirror, right? So with the convex mirror is image, if I use those 3 let's say 3 rays. Remember, convex mirror, the shape gives you such that focal length and the curvature, C, right, is in the back of the mirror, right? Because see, if I kind of continue the shape of this sphere, right? See, the sphere kind of goes like this. That means the focal length and the C, that means F and R, are in the back of the mirror. Now, ray 1 goes parallel and has to go through the focal point. But focal point is, in the back of the mirror. Also, using the law of reflection, you can see that it basically goes in that direction. Ray 2, it's the mirror and it has to go through the focal point, but focal point is on the other side. So we kind of have to basically trace those two things, right? So trace those. And what we get here is, remember, that means when this ray 2 reflects, we always use the reflected light to actually generate the image. So this is then the reflected light for this ray 2. Ray 3, which has to go to the center, so it hits the mirror, and then we assume that virtually it does go through the, let's say, center, and then reflects back. So you can see, right, all those three converge to this point P prime. Okay, all those three converge to that point P prime. And you can see that it can be then used to find the image. Image is virtual because it's in the back of the mirror. Image is upright, and all the virtual images are upright. And also it's smaller than the object, okay? So the image is smaller than the object, and this will be always true for the convex mirror. See, the convex mirror always gives you virtual, always gives you virtual. Concave mirror always can also give you a virtual. What is the difference between virtual of the convex compared to the virtual of the concave mirrors? Where virtual image of the convex mirror always reduced in size. Where we had here, right, virtual image of the, this is a concave, right? So see, this is a virtual image for the concave, and it's always enlarged. So that's the main difference. That means you can get a virtual image with concave mirror and convex mirrors. But difference here is the concave mirror always gives you magnified, larger image, where convex mirror always gives you a smaller image, okay? And convex mirror never gives you real image, okay? And it doesn't matter where you put the object. So I can put the object here, I can put the object there. Doesn't matter. You're gonna get a virtual upright and smaller, image. That's basically the case with the convex. So that's why it's kind of like a very similar to, in simplicity to the plane mirror or flat mirror. Flat mirror always gives you virtual, right? Always gives you behind the mirror, always gives you the same size and upright. Convex mirror always gives you small virtual, again, in the back of the mirror. All right. So again, so this is how you would draw the ray diagrams. It's a little bit more difficult to visualize the diagram for the convex mirror, but remember, more or less, you're assuming that after hitting the surface of the mirror, those ray 1, 2, and 3 diverge away. So in order for us sort of like go to the point F, C, they have to, kind of virtually go to that point, right? So this is, virtually, goes to that focal point. So this guy here is virtually goes to that, point C and thing like that. So because point C is on the other side. But in any ways, you can, again, using reflected ray, right? So this reflected ray, this reflected ray, and that reflected ray, to trace them back to find the image. Only the reflected rays can be used to find the image. All right, so kind of summarize everything. With the concave mirror, the image may be either real or virtual. When the object is outside the focal point, the image is real. When the object is at the focal point, is actually when we're going to see a case, right? The image is infinitely far away. That means we can say then there is no image. When the object is between the mirror and the focal point, the image is virtual. With the convex mirror, the image is always virtual and upright. And as the object distance decreases, the virtual image increases in size. All right, so let's do then some examples here. So we have a concave spherical mirror, has a radius of curvature of magnitude 20 centimeters. So find the location of the image for the object distance of 40 centimeters, 20 centimeters, 10 centimeters. Okay, that means we assume that object, it changes position, and we want to find image for each position of the object. And for each one, we're going to state whether the image is real or virtual, upright or inverted, and find the magnification in each case. All right, so remember, what we're given here is the radius of the curvature, right? So we're told that that's the radius of the curvature, and it's 20 centimeters. Okay, so here's what we have. If the radius is 20 centimeters, which means focal length, which is 20 over 2, right? Remember, r over 2, that means it's 10 centimeters. Okay, so then using the equation for the mirror equation, right? I can have like 1 over p plus 1 over f, sorry, 1 over q equals 1 over f. Okay, and you can see, right, I am given position of the focal length always. And for this part A, I'm then saying, okay, so f is given as 10 centimeters and p here is 40 centimeters. Okay, and what you have to do here is use this equation. By the way, let me give you like a shortcut equation for this. If you remember, right, so kind of similar to this has a very similar format as the capacitors in series or the resistors in parallel. That means I can, I can have, let's say, 1 over p equals, if I can, sorry, 1 over p, let's say, plus 1 over q equals 1 over f. So I can take the inverse of both sides, and in a way I have this. F is equals to then q times p over q plus p. That becomes that, just like the shortcut for those. Or now if I'm, let's say if I want to find for the, if I want to find the image position, so then what I can write here is 1 over q equals 1 over f minus 1 over p, right? If take this equation and rearrange it for the q. And if I use the shortcut for this equation, right? So this becomes q is equals to p times f over p minus f. That becomes this equation. So a lot of times, I actually would end up using this equation to do the calculation. So either way, either just this general equation, use it and find a position, or just shortcut equation. In any case, you given f, you given p, should be easy to find the q to be 13.3 centimeters. Now, that means the image, right? Image is positive. Remember, positive image distance. Image distance is positive. Positive image distance means it's in front of the mirror, which means, it has to be real. So this is, in terms of, let's say, part B, right? It says find real or, virtual. So here it's real. Upright or inverted. Well, remember, this is real image. Real image always inverted. Okay. And then we can find the magnification. So magnification, remember, is h prime over h, or negative q over p. Well, then negative 13.3 over 40 in this case will give us negative 0.333, means it's inverted because it's negative. 0.33 means it's smaller. Okay. All right, so that's, that's first one. Second one, we have then well, this is, I guess you can say, the case one. So case two, we have the object position at 20 centimeters, which you can see, right, it's equal to the radius, okay? But still it's greater than focal length. All right, so in this case, I can still, use exactly the same equations, find Q. So once I find Q, I'm gonna get Q equals 20 centimeters. Well, does it mean, say Q is 20, P is 20, that means Q is exactly the same position as P, but in front of the mirror. Well, it's, if it's positive, that means it's real, and it's inverted. Okay. what will I get for magnification? Well, remember, if it's negative P over Q, it's negative 20 over 20, I get negative 1. Okay, so I get negative 1. That means it's same size, it's just, inverted, right? Then let's look at, case 3. So case 3, I have P equals 10 centimeters. Okay, what do we get here? Well, remember that shortcut equation, Q is equals to P times F over P minus F. So P is 10 and F is 10. So it's 10 times 10 over 10 minus 10. We get, 100 over 0. We get infinity. What does it mean? Means no image, or image is infinitely far away. But generally what we say is that there is no image formed. So there will be no image for this particular case. That means as soon as you put the object, if you have a curved mirror, right? If you go and stand in front of where the focal length is, focal point is, there will be no image. There will be no image. And before that, your image will be inverted. After that, your image will be then upright and magnified, because then you get a virtual image. All right, so let's look at another example here. A convex spherical mirror has a radius of curvature of magnitude 40 centimeters. Determine the position of the virtual image and the magnification for object distance of 30 centimeters and 60 centimeters. Are the images in parts A and B upright or inverted? All right, so what we're given here is convex mirror. That means we always know the images, are virtual and upright. But we're given the curvature, the radius of curvature, is 40 centimeters. But remember, because technically this is a spherical mirror, the radius is negative 40. We were given the magnitudes, right? So you have to be careful of that. Which means the focal length here is half of the radius, which is, negative 20 centimeters. Because if R is negative, F is negative. Okay. Now we have object distance of 30 centimeters for part A. So part A, basically P is equals to 30 centimeters. So 30 centimeters. And I want to find the position of the image. Well, again, using this equation, Q is equals to P times F over P minus F. So it's 30 times 20, negative 20, over 30 minus negative 20. All right, so doing this calculation, or again, you can use any version of this, equation, right? You could also use, the 2 over R version of that. But, in this case, I'm going to get 45 centimeters, okay? But it's going to be negative, right? Because see, at the bottom, you're technically doing 30 minus 20, so it's 50. But at the top is 30 times negative 20, so it gives you a negative. So we get negative 45. But it's asking for the, the position. So this is, negative position, which is 45 centimeters, in the back of the mirror. Also, we want to find magnification. So for the magnification, then I will do negative Q over P. So negative 45 centimeters over 30 centimeters. And we're going to get, okay, sorry guys, I got this wrong from, all right, so this should be a negative 12 centimeters. Negative 12 centimeters, okay. Yeah, that's for the magnification. So for the Q for the part A when it's 30 centimeters in front. So then if I'm doing the magnification, right? So it will be, okay. So it will be -12 over 30, okay? And that's gonna give me 0.4 for the magnification, because negative, negative, cancel each other, right? So you get positive and you get 0.4, which means that it's a smaller, right? Only 40% of the object's height, but it's upright because magnification is positive. All right. Part B is we take P to be 60 centimeters. Okay. So P is 60 centimeters. Okay. And from here, again, I can use the same equation. Q is equals to P times F over P minus F. And this is then now 60 times -20 over 60 minus -20. Again, if I do this calculation, I'm going to get -15 centimeters. So again, it's negative, means it's in back of the mirror. And this is what we should expect anyways, right? Because it's a virtual image always. We're given that from the beginning. And if I'm finding magnification, which will be then -15 over 60. So we should get 0.25. So it's getting even smaller, right? It's getting even smaller. And because both magnification are positive, right? That means they're all going to be upright, right? So all of them are upright. Again, remember, magnification can tell you that directly. So if magnification is positive, right? Always it means it's upright. All right. Okay, so here's like last example in this case. So you have a concave mirror that has a radius of curvature of 60 centimeters. Calculate the image position and magnification of an object placed in front of the mirror at a distance of 90 centimeters and 20 centimeters. Draw the ray diagrams to obtain the image characteristics of each case. All right. So in this case, we're given radius 60 centimeters, which means technically then the focal length is 30 centimeters. And we want to find, part A, where the image P, right, is 90 centimeters. And for the second one is 20 centimeters. And you can see, right, first one will give you where the object is further than the center of the curvature. Part B gives you an object where it's even closer to the mirror than the, the focal length. So basically, you should here predict that for part A, you should get a real image, smaller. For part B, you should get a virtual image. All right, so using the calculations, so Q equals P times F over P minus F. Again, in the slides, I have different, where you can see the different way of doing this. So here I have then 90 times 30 over 90 minus 30. And we're going to get 45 centimeters. Okay. And if I want to then do the diagram, so we can do the rough diagram. So here's my lens, mirror. And this is the focal point, and this is the ray, this point C, right? And my object here is somewhere over there, right? So this is my object though. Okay. Then what I have here is, using those three rays, I can demonstrate the position. Remember, ray 1 goes parallel and then through the focal point. Ray 2 goes through the focal point, then parallel. And then third one goes through this, this C point, and it reflects back to that C point. And then you can see the point where they converge, right? And that's basically going to be my image. Okay. So that's where my image will be formed, right there. Okay. So it's going to be smaller, right? Inverted, and it's a real image. Okay. Part B, we have then P is equals to 20 centimeters. Well, I can calculate Q, which is 20 times 30 over 20 minus 30. And remember, even if you get a virtual image with the concave mirror, R and F always positive. All right, so if I do this calculation, then I should get negative 60 centimeters. Okay, negative 60 centimeters. By the way, let's say if I do the magnification for this guy, so magnification equals, let's say, negative 45 over 60. So if I do the magnification, oh, sorry, P is 90, negative 45 over 90. So I'm going to get a negative 1/2, right? So that's basically going to be for the magnification. All right, so here also, if I do magnification, negative Q over P, so I get negative 60 over 20, right? So you can see that negatives cancel out, 60 over 20, you get 3. That means you're going to get 3 times bigger, image. Okay. And for that, again, what we do here is, I should probably do this because image going to be in the back. So something like that. This is my mirror. And let's say this is my object. So remember, this is C, this is F, and now my object is right here. Okay, my object is right there. That means what I have here is this. So remember, ray 1 goes parallel, then it has to go through the focal point like this. Okay. Then the other point is going to go hit the mirror and then reflect. All right, so let me try to do a little better job with this one. All right, so gonna go hit and then go to that point C. Even worse, but all right. And that means from here, just those two alone, right? By the way, this point is known as a vertex, and I can also use that point. So let's say there's a, hits the point of vertex and then reflects back like this. And then I can, let's say, trace that, trace this, and trace that. And then you can see, right, my image is right there. I could have probably gone a bit more, but my image is right there. So it's virtual in the back, and it's much bigger than the object. All right. All right, so next we're going to talk about images formed by refraction. So we're going to consider, objects that allow the light to propagate to the other side. That means we're talking about now refraction. And, basically starting from this section and continuing in this chapter, we're going to be then kind of, understanding that when the light hits the surface of material that allows the light to propagate, some of the light is reflected. Some of the light is reflected. But we don't care about this reflected light anymore because we're going to concentrate on refracted light because the images will be formed by this refracted light, not the reflected light anymore. So that means the outgoing, right, refracted light is going to be used to, generate the images. So reflected light, which will always be a little bit of reflected light here, going to be completely ignored. All right, so here we have two materials. That means one is, let's say, air. The other one could be glass, right? So you have, two different index of refractions. There is a boundary line between the surfaces, right? Here, just that it's curved, right, compared to what we had before. And assume that the object at point O is in the medium, which index of refraction of N1. That means the object is always going to be in N1, and image, let's say, will be formed in, N2, or depending, let's say, on the curvature of the surface. It can also be, formed in same, let's say, same surface as the object, right? So in that case, basically gives you a virtual image. So remember the Snell's law, right? It's n1 sine of theta 1 equals n2 sine of theta 2. So for this type of, let's say images, and this is, this is a little bit different from the actual thin lenses that we're going to consider a little bit later on. Here we're assuming that the image will be formed in a different material than air, right? So that means, let's say you have object in air and image will be formed in this medium 2 and in this N2. But again, so you have Snell's law, and then what we do, because the angles are small for paraxial rays, parallel rays, we use the approximation where sine of theta approximately theta, which, modified all this, then it gives us n1 theta 1 equals n2 theta 2. And then we're going to use this to modify our, mirror equation. And this is going to be for the then refractive equation, right? So this is for the lenses as well. So, but for this particular one, it's modified because now you have index of refraction 1 and 2 different. So it becomes n1 over p plus n2 over q equals then n2 minus n1 over r. Okay, that means what we get here is assuming that you have two different materials and n1 and n2 are not the same, right? And what you get here is r is the radius, right? So you can see, right, is the radius, right, of this curved portion of this medium 2, right? And let's say this r then can be used let's say in this equation, right, with index of refraction with the position p and q, right, to find, let's say, where the image will be formed. Okay, there's also magnification equation, which is a little bit modified from the mirrors, right? So then m equals negative n1q over n2 times p. Okay, so this two equations, right, so you can say equation 1 and 2 go together to find the image for this type of case. Okay, so let's say, for example, one important thing about this type of problems is that if, let's say, I have flat surface instead of the curved surface, then r basically goes to infinity. Remember, the r is infinity if it's a flat surface. So then on the right side, you have, n2 minus n1 over infinity, which will give you 0. That means this equation modifies then n1 over p plus n2 over q equals 0, right? Means that n1 over p is equals to negative n2 over q. So then you can use this equation for flat, let's say, surfaces. Okay, flat surfaces. And there are some applications of that. So let's say if you want to find a position of the fish inside water, then you use this equation because the surface of the let's say lake, right, is flat. So, but you are looking at something that is in a different medium, right? Fish is in a different medium. You're in air, fish is in water. So you're finding the image of an object that is in a different medium. Or maybe, let's say you're inside water, you see a bird, in air, you want to find the position of the bird in air, right? And then you can find that. So that also a case, let's say, where, you can use this equation. So again, so that's kind of like, those are some nice examples that you can use for that. So for example, if it's a flat surface and there's a fish over there, right? So if you're trying to find the position of the fish, so this being the P for which is position of the fish, but position of the image of the fish, then you're going to be using this modified equation where you take r to be infinity. And one of the things we're going to see here is when the light comes out, it's going to bend away, right? So if you trace them back, actually fish will be somewhere over there. So we're going to have a closer distance from, or appear to be closer to the surface than it really is. Anyway, so this type of problem, right? So we use sign convention that apply to this equation. So note that real images are formed on the side of the surface that is opposite to the side from which the light comes in. That means the same side as a refracted light. That's now is the positive direct side. Remember, for the mirrors, the front was positive. Why? Because that's where the light was reflecting, right? And the entire light was reflecting. So, but here light is refracting to the other side, and the other side is then positive. That means opposite to the side from which it comes in. That means incoming, which is on the left side, and refracting on the right side. So that means the right side is now a positive side. Okay, that is in contrast to mirrors, again, because mirrors take, a front as positive, back as negative for this refraction, right? So basically, again, we assume there's a different medium, right? So this is the negative, this is positive sides, always. Okay, even if it's, let's say, a flat surface. So if this is a different medium, this is negative side, this is positive, because the light will, refract, right, to the other side, let's say. That means the same side as the incoming light becomes a negative side, right? Again, so this table gives you that. So object location, so it's positive when object is in front of the surface, okay? Negative when the object is in the back of the surface. So this is usually used when the, let's say, image of one is considered as the object for the second surface, something like that. Then you might have something like this. Image location. So image is positive when it's in the back of the surface. Again, back of the surface, remember, it's a positive side. And image is in front of the surface, it's a virtual image, because you can have image formed in front of the same side as the incoming light, but in this case, that's a virtual image. And then the image height, h prime, so image is upright, it's positive. Image is inverted, is negative. Basically same as mirrors. Radius, so the center of curvature is in the back of the surface, then it's positive, which is in contrast with mirrors. And the center of the curvature is in front of the surface, then it's negative. Again, in contrast with the mirrors. Make sure you guys are comfortable with this. All right, so this is kind of what I have, right? If refracting surface is flat, r approaches infinity, then you end up with those two equations. So this is basically modified equation, and this is for the image position. So Q equals negative N2 over N1 times P. That means the image formed by a flat refracting surface is on the same side of the surface as the object, always. That means that if there's a fish, if you're from air looking at the fish who's in water, image will be in water, same as the object. If you're inside water looking at the bird who's outside in air, image of the bird will also be in air, because the image is formed by a flat refracting surface is on the same side as the object, always. And virtual image is always going to be then virtual. Okay, but then one thing we can also do here is we're going to now concentrating on curves type of, this is a reflected rays intersect different points of the principal axis. So what we're doing here is we're going to look at, so let's say for this type of thing, and then we're going to consider thin lenses where it's a little bit, different in terms of what we'll have where the image will be. All right, so one end of the long glass rod, where the index of refraction is 1.5, is formed into a convex surface with a radius of curvature of magnitude 6 centimeters. An object is located in air along the axis of the rod. Find the image positions corresponding to object distances of 20 centimeters, 10 centimeters, and 3 centimeters from the convex end of the rod. Okay. So this one, I just noticed I didn't have enough room, but so remember, we are using this equation, right? Because it's a refraction, and it's basically simple enough that I can then use it. So remember, so N1 is air, so it's 1, and 2 here is 1.5. So in this equation, we basically replace all of those, and remember, R was given as 6 centimeters. Okay. So we can just do this calculation and have then, this is, as a template. And then from here, all we have to do is just, rearrange and solve for Q, because we also given for part A, let's say P is 20 centimeters. For part B, P is 10 centimeters. And for part P is 3 centimeters. Okay. And what we get here is for part A, if you do the calculation, we get Q equals 45. Okay, Q equals 45 means the image here is formed in the same side as the outgoing light, right? So basically it's in the inside the the object. sorry, inside this medium tube. All right, so but for the part B, you get Q equals negative. So that means this is a negative image distance. So part C will also get Q equals negative 60, which means, remember, if the position of the image is negative, that means the image is in front of the surface, okay? That means, for example, right? So let's say here's the rod in each case. So here, the image will be formed inside, so somewhere over here. So for the second case, image will be formed, you know, in front of the, let's say, so this will be Q, this will be Q over there, right? In front of the, you know, surface, and then here also in front of the surface, somewhere over here. That means for A, image is real. For B and C, images are virtual, because Q always negative for a virtual images in this, you know, in both mirrors and lenses technically. So if the Q is negative, right, that means you always get a virtual image, right? You get a virtual image and it's in front of the surface in this both cases. All right, so then what we have here is the last thing we're going to consider, basically thin lenses. Okay, so typical thin lens consists of piece of glass or plastic, something like this. So if this was kind of like the plastic rod that we considered before, now what I do here is I take the surface and I carve another one like this, and then get rid of the rest of the stuff. That means what I have here is I have a very small very small piece of, you know, than this plastic or glass. Okay, so you can say it is ground so that the two surfaces are either segments of a sphere or plate. And lenses are commonly used in optical instruments such as cameras, telescopes, microscopes to form images by refraction. Okay, and then depending how you carve this, right? So you're gonna get either like this, or maybe you can carve it like this, right? And have two types of lenses. And let's say here are some types of lenses. So mostly we're gonna be using biconvex or just convex, right? And bioconcave, which is like this. That means, see, if you have this shape, this is known as a convex lens, or we're going to call this converging lens. So both of their names are correct, convex or converging. And then if you have this shape, so this is, so it says bioconcave. Bio means that both sides are kind of concave like this, right? So this is known as a just concave lens or diverging lens. Okay, so concave or diverging lens. And see, this is convex. Concave means that, you know, one is concave, one is convex. Plano convex means that this is convex, here is plane or flat, right? So you might see something like that. So generally what we have here is, let's say here a radius is positive, it has a radius, well, let's say not equals to 0, but for this the other surface radius equals 0, oh sorry, infinity, right? So you kind of have that. All right, so then what we have here is the next few slides basically goes over how to find the image with this, you know, types of, you know, thin lenses, okay? Because the difference between refraction, where the image, you know, like let's say the previous few slides, right, where the image is actually can be formed inside the glass. Here we assume that there's never the case. That means light will always come out of the glass because glass is very thin. All it does is it redirects the light so that kind of converges at some point. But image will always be formed in air, okay? Either real or virtual, right? So let's say we assume that it's never in the glass itself, okay? So this is one of the cases where we can have, for example, when the image is really far away, when we can say that P here is at infinitely far away, then light rays from that come parallel to one another. And then the lens then makes it converge to some point f2, which is the focal point. Remember the mirrors had a focal point. Well, lenses also have focal point, but they have two because they have on each side. So here's the lens. See, you can see things like this is one curvature. So there's a focal point there. And then here's the second one. And there's a focal point over there. Okay, so you have then f1 and f2. So you have kind of like two focal points for the thin lenses. All right. So then you can see, right, you say lenses will have one focal length. That means they have the same distance, but two focal points. Okay, and we're then gonna look at in terms of what this is type of let's say called converging lens, because you can see the light converges when it goes through the lens. So it converges to some point in in the same side as a refracted light. And this is an example for the diverging lens. When taking the p equals infinity, the light rays are coming like parallel to one another. See, after hitting the lens, right, they refract, but they refract such that they diverge away on the right side, right, in the back of the lens. Well, when they diverge away, they're never going to converge to some point to form an image. So what we do, we take the refracted light, we trace them back, right? So we trace them back to get the image. So let's say the refracted, trace them back, trace them back, trace them back to form an image, okay? And in this case, if p is equals to infinity, then q here is equals to that same distance as f, right? But in this case, what we have here is f is negative, q is negative, because it's going to be a virtual image. All right, so we'll do some examples of that. But here what we get is the magnification equation and what we call thin lens equation. And you will see it's the same equation as the, mirror equation. So they are pretty much the same. So magnification equation has a ratio of h prime over h and negative q over p. And the thin lens equation is 1 over p plus 1 over q is equals to 1 over f. And here's an example how to find the image if you have a convex or convergent lens, right? So you can see that here's the object, okay? And you can see, right, I'm using two rays. So let's say this is ray 1, this is ray 2. Here, ray 1 goes parallel to the principal axis. Then it has to go to the focal point just before. Now it refracts to the other side, right? So it goes parallel, then goes to the focal point. And then another one, which is basically goes to the vertex. So this one, as it goes to the vertex, and it's a nice one because it never changes direction, just goes in a straight line, continues like that. And you can see, right, those two converge at that point, and that point is where the image is. So you can also do, let's say there's a focal point on this side as well, remember? So you can also use another line, another ray that goes through that focal point and then goes parallel to the axis. You can see, right, it also converges, or intersects with those at that point. So that's where the image will be. You can see, right, it's a real because actual ray goes through that, it's inverted, and it's kind of like comparable in size. But that size can change depending where you put the object. All right, so let's first understand in terms of how to do the design convention, right? So see, the thin lens equations can be used with either converging or diverging lenses. If we adhere to set of sign convention. Remember, as with mirrors, we call the side from which the light approaches the front of the lens. So this is the front. And the other side then is the back of the lens. Note that converging lens has a positive focal length under this convention, and diverging lens has a negative focal length. So this will always be true, just like let's say concaves and concave mirrors, remember? So a concave mirror always had positive F, positive R. Convex always had negative F, negative R. Same thing is here. So if you're talking about converging lens, which is a convex lens, so it always has a positive focal length and positive radius, where the diverging lens has a negative focal length. The radius is a little bit more complicated for the lenses, and we're going to see why, because they're technically, each lens has two radiuses, right? But let's say things like this: the focal length, right, is always positive for the converging or convex lens, and focal length is negative for diverging or the concave lens. All right. So the names positive and negative are often given, to these lenses. So you can see, right, P is positive if it's in front of the lens, but Q is negative if it's in front of the lens. Because in this case, more or less, the front is always going to be the negative or virtual side, where back is always going to be the real or a positive side. Because Q, if it's formed in the back, that's going to be a real image, and it's going to be, in a positive side, right? Q will be positive. Okay. P is negative if it happened to be in the back. So again, this is usually works when you do two lenses, and lens one generates image where in the back of the lens two and things like that. But we're not going to be doing two lenses in this class. Okay, so make sure you guys are comfortable with the sign conventions. Okay, so again, this table gives you all of those values, right? Object location, image location. So let's say, again, image, right, is in the back of the lens, always going to be real and positive. Image in front of the lens, always going to be negative, and it's virtual. Image is upright, positive. Image is inverted, negative, just like the, for the mirrors. See, here you have R1 and R2. So the center of curvature is in the back of the lens, right? Center of the curvature in the back of the lens, if for the positive, and center of the curvature is in front of the lens for that to be negative. So we're going to cover that a little bit more detail later on. Well, so then focal length is always positive for the converging lens, which is, remember, is a convex lens, and it's always negative for diverging lens, which is concave lens. Remember? All right. So on top of that thin lens equation, we also have another one we call like lens maker's equation. So for this, see, I can add 1 over P to 1 over Q to get 1 over F. But there's another equation also to find this 1 over F, which is the right side of the equation. And it is N equals 1, and N is the index of refraction of that glass, right? And then times 1 over R1 minus 1 over R2. You have to understand that R1 is the radius of the curvature of the front surface, and R2 is the radius of the curvature of the back surface. And then here you have, right, if the center of the curvature is in the back, it's positive, and if it's in front is negative. So then what you have here is, you can say, right, so R1 is positive, R2 is negative for the converging, and R1 is negative and R2 is positive for the diverging lens. So then in this parenthesis, you never get 0. So one of them, see, because if R1 is positive, R2 negative, so then you have negative, negative, so you don't get 0. And if this is negative, so negative minus positive, then again, you don't get 0. So you have to be careful with this because this parenthesis never gives you 0. So if one is positive, the other one negative. If one is negative, the other one positive. It's kind of like always like that. All right. So the image formed by thin lenses, you can see, right? So we can also use the ray diagram, right, on top of those equations. So to locate the image of converging lens, the following 3 rays are drawn. So we have ray 1 is again parallel to the principal axis, then passes through a focal point on the back of side of the lens. Ray 2 is drawn such that it goes to the center of the lens and continues in a straight line, which is the vertex point, right? And ray 3 is drawn such that it goes to the focal point on the front lens and emerges parallel to the principal axis, like I did last time. So here's an example of that. So ray 1, you can see, right, parallel and through the focal point 2. Ray 2 through the focal point 1 and parallel. And ray 3 goes through the vertex. Okay, so this being the vertex. So if I do that for the converging lens, then what I get from here, if the P is greater than F, this is basically what we're going to get always. So we're going to get image that is, you know, in the back of the lens, and it's going to be real, it's going to be inverted, and again in the back side, right? And size can vary. Further you are from the point F1, smaller the image. Closer you get to F1, you know, bigger the image gets. So that's kind of like what we get. And if I eventually bring the image, sorry, the object to F1, well, if I bring the object to F1, then we get, you know, image. So if P is equals to F, right, then Q here becomes infinity far away. That means you say that no image. And you can say that from the equation, right? 1 over P plus 1 over Q equals 1 over F. So if I do that shortcut, P times F over P minus F, well, if P and F are the same, then you're dividing by 0, which gives you infinity. You can also continue, let's say, and move the object closer to the lens. That means now P is less than F. Well, in that case, you get then a virtual image. That means converging or concave, sorry, convex, right? Converging or convex lens can give you a real or virtual or no image, just like the concave mirror, okay? So again, here you have those 3 rays. So parallel through the focal point. The other one has to go to the focal point F1, but it's in front of the F1, so it kind of, you know, have to be traced back, you know, virtually. So here's F2, then remember you took F2, you know, so this ray 2 and refracted ray, you trace it back. Then refracted ray, trace it back. And this one, the center goes like this, and you trace it back, and there where the image is. Image is virtual. Why? Because it's in front of the lens. It's upright, which you can see from the diagram. It's larger. Again, you can see from diagram, or you can calculate magnification and get maybe like, let's say, +2. Plus means it's upright, 2 means it's larger. And image is on the front side. How do we know in terms of calculation? Well, Q will be negative. If Q is negative, right, that means it's in front of the lens. All right. So then for the diverging lens, basically, again, same thing. Same 3 rays can be used to find the image. But the difference here is you get always just the same thing. So let's say here's the object. See, 1 ray goes like this, and it has to, you know, when it comes out of in the back, it has to, it diverges away. So you have to, you know, take that refracted light and trace it back. Then this goes to the vertex, right? Kind of goes like this, right? And the other one goes, it has to go, let's say, through the F2, but it doesn't directly, so it actually refracts like that. So you kind of trace it and take the refracted back, and they all converge at this point, and that's your image. So it's a virtual image because it's in front of the, you know, lens. It's upright because let's say H prime will be positive and magnification will be some kind of positive number, but it will be positive maybe 0.5 or something like that, because always going to be smaller, and, you know, in front of the lens. Okay, so that means this is always true regardless where the object is positioned. No matter where you are, you're always going to get this. All right, so for converging lens, when the object distance is greater than the focal length, so that was the first case, right? The image is real and inverted. For the converging lens, when the object is between the focal point and lens, which is P less than F, the image is virtual and upright, and also, you know, bigger, right? So that means one thing important to understand, that virtual image created by a converging lens, right, is bigger. Oops. It's always going to be bigger compared to the let's say, the virtual, generated by the diverging lens. That means what we have here is for diverging lens, virtual image always going to be smaller. So it's still the same virtual and upright, but it's smaller. Virtual image generated by the converging lens is virtual upright, right? But it's always going to be larger. That's how you know which one it is. Okay. So let's look at this example here. So I have the work, but we should be able to follow it. So the left face of a bioconvex lens has a radius of curvature of magnitude 12 centimeters, and the right face has, curvature of magnitude 18 centimeters. The index of refraction of the glass is 1.44. Calculate the focal length for light incident from the left. Well, remember, we are given in terms of the radiuses. We don't know where the object is positioned, and we don't know where the image is. So, but given with the radius 1, radius 2, and the focal length, we can use then Lensmaker's equation to find f. Remember, for the convex, R1 is positive, R2 is negative, always. For convex lens or a converging lens, right, that's the case. And remember, if you have a concave lens, then it's opposite. R1 is negative and R2 is positive. So now, because we have a convex, then we use basically R1 positive, R2 negative, and then so R1, which is 12 centimeters, and R2, which is 18, we're given the magnitude, so plug in negative 18 and calculate the focal length of 16.4. All right, so here's another example. So we have an object that is located at 20 centimeters to the left of a diverging lens, having a focal length of 232 centimeters. Oh, sorry, there's a typo. It is actually just a 32 centimeters. All right, so 232 is too much, so 32 centimeters. Determine the location, the location and the magnification of the image, and construct the ray diagram. So the ray diagram is already constructed for you. So remember, you do the easiest one is do a P, the ray 1, right, parallel, then it diverges away, but it has to go through the focal point, so you kind of trace it back. And the other one is the, ray 2. I usually call this, V ray, because it always goes to the vertex. And you can see, right, both of them then converge at that point, and that's where your image is. And you can see, right, it's smaller, and it's upright, and it's virtual because it's in front. And then we can use this equation, right? 1 over P plus 1 over Q equals 1 over F. And I can just use this, equation where I have Q is equals to P times F over P minus F, right? So plug in the values, right? And we should get negative 12.3 centimeters. So that's the image position. Again, it's negative because it's in front of the lens. Now, magnification is then negative Q over P. So the negative 12.3 over, then object is 20, remember? So 20, and we're going to get 0.615, right? That means it's upright because it's positive, and it's about 61% of the object. That means it's, again, it's smaller than the object. All right, so this concludes this chapter. So make sure you guys are working on the homework problems. Chapter 20, next chapter, chapter 27 will be posted shortly.